Hello, ladies and gentlemen. Welcome back once again. I am your host, the Economancer. We're going back to the 6th edition of Peter Kennedy's A Guide to Econometric. This is very important. So, what this is going to be going over is classical linear regression model. And most importantly, those assumptions that are associated with the classic linear model. Now, why does this matter? Well, a lot of people may understand probability and they may understand statistics. They may get what's going on here. But when it comes to the finer understanding of all of this, because again, this series is not about getting a graduate level education or even an undergraduate level of education in econometrics or statistics or anything like that. This is about grasping the concepts and the understanding of what's going on, especially when you're reading something from like a piece of literature or you're reading something in the New York Times or something like that, and they're saying, well, oh, they have this new uh, paper that came out that gives this information, and you're like, okay, well, I don't know what's going on here per se, because I understand probability and I understand statistics and I get linear regression for the most part, right? We're just summing it up and then finding the distance between those squares to be the smallest, and then boom, we have our ordinary least squares. But what's going on with all of these other stuff? Why are we doing all this other stuff? And this is where understanding the classical linear regression model matters the most, especially when we're thinking about things like linear to nonlinear regressions, endogeneity, heteroscedasticity, and Kuznets curve. And I'm going to be trying to explaining this. It's going to be bouncing around a little bit in this slideshow, and that's mostly because there's a lot of things that I'm going to be talking about, and then I'm going to be referencing back or through. And that's just go with it. Go with it. So let's just start off with, the classical linear model, the classical linear regression model. It serves as the optimal estimator under specific conditions, conforming to these 5 assumptions in the data generating process. So a violation of these assumptions diminishes the reliability of the classical linear regression model. So it's no longer the optimal estimator. So consequently, econometric cues and stuff like that often arise from a breach of at least one of these assumptions. So why researchers are doing something outside of classical regression is because one of these assumptions have been breached. So researchers typically start their investigation with the classical linear regression model and its assumptions, and then they explore any deviations, assessing whether they can be remedied or if some alternative estimators should be employed. And that's very important to know. All right, so what are those? You can see here, so it's linearity in parameters, zero expected value of disturbance terms, homoscedasticity of disturbance terms, fixed explanatory variables, number of observations exceeding the number of independent variables, and multicollinearity is associated with that. All right, so linear in parameters. So that is this graph right here. Really cool, right? We have x. As x increases, so does y. That is a linear determination. That means the dependent variable is calculated as a linear function of those specific independent variables plus some noise. In this model, I don't have any noise because it's perfection, which is not real. So is it a real thing? Anyway, so the model's unexplained variance is captured in this beta coefficient, right? So if you have boop, 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 that beta coefficient, that beta naught, that is where you're going to have that unexplained variance captured. So errors can occur when essential independent variables are overlooked. So this is omitted variable bias, or when irrelevant variables are included. So let's give an example of this linear in parameters, right? So suppose you're examining income inequality in the United States and one of your variables is favorite color. So common sense would dictate that this variable is likely irrelevant to income inequality and it should be removed. There might be instances where the relationship between the independent and the dependent variable is nonlinear. This leads to changes in the beta coefficients over time. The Kuznets curve is a prominent example of nonlinearity with varying applications like the environmental Kuznets curve, the crime Kuznets curve, and the original income inequality or growth and development Kuznets curve. All of these models indicate an increasing function. And so what that looks at. So we can see here, this is the original Kuznets curve. What this says is as your civilization grows and you get more economic growth, you start hitting to some precipice of development. Once you hit that level of precipice, you're actually going to have a decline in the amount of income inequality. So as your country grows and as you have more technology and stuff, income inequality is increasing. This is due to the division of labor and stuff like that. At some point, it starts to decline and you start having less income inequality because now your civilization cares more about what's going on. And so they're more likely to increase taxation, move towards a higher taste of redistribution, et cetera. And all of these impact that income inequality metric. There's the crime Kuznets curve. Again, this is something that shows like a certain level of economic growth leads to a certain level of economic development. And once you hit that level of economic development, you're more willing to put in resources into reducing crime, whether that would be healthcare or mental health and other types of healthcare, whether that comes in the form of like better education, whether it comes in the form of more jobs, so more people have jobs, so they're not as apt or as likely to get into crime and stuff like that. And then they're the environmental Kuznets curve. And I'm pretty sure if anybody's ever watched any of the videos with Jordan Peterson, anytime he talks about this environmental ilk and stuff like that, he always brings up the environmental Kuznets curve, which he doesn't really call it that for whatever reason. Well, at least I haven't seen him, but I honestly don't watch him very much anyway. So, you know, that's up in the air. But really, this is the case that there's a lot of these realities, I guess you could say, that show over time there's changes. And this is a non-linear case when we're trying to evaluate classical linear models. This is just going to violate those assumptions. Also, something to think about when we talk about these Kuznets curve, there's actually a Kuznets wave that happens as well. That's something that's looking at some of the more recent GDP to income inequality data, that it actually fluctuates over time and rides on this Kuznets curve. So once we hit some bottom, we start going up, and it's not a U-shaped curve, it's a sine cosine function. It's a wave. And this is really important if you're doing any like long run evaluation of GDP, income inequality, or any of these other metrics, because it shows that it's not a certain level of development. It could be a certain level of technology. Like a technology shock would have an impact on this. Okay. So now we're going into zero expected value of disturbance terms. There's really not a whole lot to say here other than this assumption is that the mean value of the disturbance term is 0. So violation of this assumption, as I was stating earlier, might result in a biased intercept. All right, now we're moving on to homoscedasticity of disturbance terms. So this assumption postulates that all disturbance, so I think we got this. Yeah, we got this. All disturbances possess the same variance. So a violation results in heteroscedasticity, where the error term's variance, conditional on the explanatory variables, differs for various combinations of the explanatory variables' outcome. This does not cause estimator bias. However, autocorrelation, where disturbances correlate with each other, often appears in time series regressions and is useful to determining stationarity, which is something that we'll get into over time. But as you can see here, we have our predicted values on our x-axis and we have our residuals on our y-axis. They don't seem to be matching very well. I'm sure plenty of people have seen different plots of the residuals versus the predicted. I think one of them is like a QQ plot and stuff like that. But the key here is to understand that this doesn't bias the estimator, but it does impact the estimator's ability to like do something good when it comes to predicting or when it comes to understanding what's going on with the data generating process. So anytime you see this, you definitely might want to look at a way to go about dealing with this problem. And again, now we're going into fixed explanatory variables. So this assumption implies that explanatory variables are fixed and repeated samples. It encompasses issues like measurement error in the independent variables and situations where a lag dependent variable is used as an independent variable. Essentially, this value is deterministic and uncorrelated with the error. So there's a complex relationship between how closely your data aligns with a randomized control experiment and the methodological complexity needed to analyze that data. And again, if anybody's ever seen any of my videos on talking about Ashby, this is one of those things where this is a violation of Ashby's law of requisite variety. However, it is also acknowledged that these randomized control experiments can still grapple with internal and external validity due to the likely correlations with unobserved characteristics. This is the Hawthorne effect. So we have non-representative samples and other general equilibrium that gets brought up into this. And so if you're looking at a closer research design, this really becomes the bright line. This randomized control experiment is the bright line. But we have to understand that the difficulty of these randomized control experiments, they can be increased by stratification, pairing, clustering, etc. And so when we're moving to our second part of inference when it comes to these randomized control experiments, as well as the other part, right? An estimation of these heterogeneous treatment effects with many covariates by identifying some subpopulation with different treatment effects to maintain these valid confidence intervals. This is what causes these randomized control trials to struggle with this internal and external validity, right? Because there's likely correlation with unobserved characteristics. And since we have this statement that randomized controlled experiments are the baseline for causal analysis, we have to understand what's going on when we compare it to ours. And the way I tend to think about this is like by proof, right? So suppose there is an inverse relationship between how close your data is to a randomized controlled experiment and the complication of the appropriate methodology for which to analyze the data, right? So by contrapositive, we evaluate this P implies Q statement. By abbreviating the statement, we find random moves to less complicated. So the more randomized it is, the less complicated it is to do the methodology or to do the econometric method to it. Thus, the inverse of this statement is not random, not less complicated. So the contrapositive becomes not less complicated, not random. Therefore, we can say that given the inverse and the contrapositive are both true, then the conditional statement is true. Now, again, we can make some cheeky jokes about this, but really, the more closely a data set is to random controlled experiment, the less rigorous the methods are needed to study the effects. That's why when you're looking at some of this stuff and we're like, oh, well, they're not fixed. Because the more they're not fixed, the more stuff you have to add into your econometric tool bag to deal with it. So the element of control here is to reduce the likelihood that exogenous forces affect the outcome of variables. So again, when we're looking at this, this is very important because if you're reading a paper and they're not taking into account stuff like endogeneity, or they're giving you very plain readings of the data generating process and you're looking at it going, I think there may be some mix up here. I'm not sure how all of this goes without really understanding how we're not controlling for possible exogenous shocks when we're doing these classical linear regression models. You obviously need to do something more. And then you read something and you're like, okay, well, they're doing two-stage least squares. Why are they doing that? Because they have this explanatory variable that's not fixed, or it even doesn't even exist, and they have to operationalize something in its place, so on and so forth. So a lot of this gets brought into account. So if I have this, no, I have multicollinearity, which is the next one. So the number of observations, right? This assumption is straightforward, but it's crucial when working with small sets of data with numerous explanatory variables. I've seen this many, many times where people have this huge expanse of variables and they'll try to capture as much information as they can out of these variables, and it's only got like 5 things, but they've got like 20 variables. This is bad. This violation of the assumption results in multicollinearity. where there exists an exact linear relationship between the independent variables. So it's important to identify and rectify this by dropping certain variables. And a lot of people don't realize that this is a big problem. So the best way to think about it is, so essentially, there's no exact linear relationships between the independent variables and more observations than the independent variables, and this is what we call multicollinearity. Again, what's often called multicollinearity is really micronumerosity, and that just means that by the assumption that there's a perfect linear combination of some of the other independent variables in the regression, it's usually due to low amounts of data used in trying to capture a data generating process. So again, if we have a data generating process that starts at the beginning of time, we can make that case, right? And then we're only taking like a snapshot of 2 years of that. Well, obviously, you're not going to understand what's going on very well. And so you're going to get regressions where we have an R squared of something like 0.95. It doesn't mean that it's perfectly linear, and it doesn't violate the assumption, but it shows you that you're probably not capturing enough time. So an important part of understanding this collinearity from a theoretical perspective is something like, let's say we're writing a study on grade point average. And in this, we have GPA as our dependent variable, right? And so we have our constant or intercept or whatever you want to call it. And then we have beta 1 or beta X, which is how much time the students study. Plus we have beta 2, how much time the student works. And then we have beta 3, which is leisure. And then we have beta 4, which is sleep plus some error term. So we have perfect collinearity between sleep and leisure because they are functionally the same thing. Because if you're having leisure, then you're sleeping. So the sleep is nested within the leisure. So if you're looking at it from a purely data generating process, they're going to be collinear. So to fix this, you could drop one of the major variables from the model. And because we assume leisure and sleep are functionally the same things with respect to studying in this study, therefore we can rewrite the equation with just leisure. However, this is where theory comes in, and it's really important to understand the theory that's being used by yourself or by those who are writing the study, because this matters. The importance of understanding of what exactly is studied in this study is of the utmost importance. So if you're trying to look at the study, the impact of studying on GPA, then it would be best to just leave out sleep in general. But if you're looking at the impact of sleep, then it may be best to try to figure out a way in the data generating process or how you're cleaning the data, etc., to show that leisure is nested. And so we don't need to just remove leisure, or we can set it leisure up as something that is not in opposition to sleep, so it's set out itself in time. So we can just assume that you have leisure as 14 hours of the day. Then you have sleep nested within that leisure of 8 hours. So if you could separate the sleep from the leisure and use them as two different variables where one isn't nested in the other, then you no longer run into this problem, and then you would be able to study the impact that sleep has. But again, a lot of this comes down to understanding what's going on in your data, what's going on in your theory, and being able to match your theory to the data generating process. All right. So now we have the criteria that we had brought up in the previous episode. So how does the OLS, ordinary least squares that we're talking about right now, how does it fulfill those 8 criteria? 1, of low computational cost. Look, the calculation of OLS involves like basic mathematical operations. In fact, you can do this as a student at like 7th and 8th grade, maybe earlier. In fact, some of the more hardcore OLS derivations that you would do, you'll do that in Calculus 3, where you'll like take foam poles and something and draw a straight line between them, right? These are not advanced calculations. They're not advanced mathematical operations for a computer. It can do them fairly easily. So there's little to no computational cost. So optimal usage of least squared. So again, optimal usage of least squared. OLS by definition is the best at reducing the squared deviations. Seems pretty straightforward. maximum R squared. Again, the R squared value is highest in the OLS due to the method's proficiency in minimizing the square deviation. So again, this is one of those, there's no violations of the assumptions, it is the best at it. Unbiasedness. Given the assumptions, OLS provides an unbiased estimate. And I was talking about earlier, some of them, even some of those violations don't actually bias the estimate, but there's still other ones. So then we have blue, right? So this is the best linear biased, unbiased, biased estimator. So if we assume the disturbances are normally distributed, this has the smallest variance covariance matrix and is therefore blue. Number 6, this is always fun. Asymptotic properties. So this becomes even more crucial. Essentially, this assumption ensures that there are no exact linear relationships between the independent variables, and there are more observations than independent variables. Violation of this assumption leads to, again, multicollinearity that we were talking about. And so it's very important to look at these asymptotic properties. Actually, you know what? I think I skipped one. All right, after blue, we go to mean squared error. So OLS isn't necessarily optimal when considering mean squared error. So a slightly biased estimator can reduce the variance, which could lead to a lower mean squared error. That's the one place that the OLS is not king. Now, if we go to asymptotic properties, if we suppose an infinite sample, OLS is asymptotically unbiased, assuming all assumptions are met. Moreover, the variance covariance matrix of the beta OLS goes to 0 as the sample size approaches infinity. This is very important when we're talking about how we deal with everything, because the more data we can get to use OLS, the better our OLS gets at being able to deal with the information. All right, and the last one is maximum likelihood, and I dropped mean squared error from this just because it actually doesn't do well in this criteria category. Probably should have had a slide for it, but you know, whatever. I'm not perfect. Don't judge me. Actually, judge me. Tell me down in the comments below how you hate me. Which, by the way, if you're watching this, like, share, subscribe. Actually, don't share it too much because I don't want to get too famous. I would hate for that to happen. Anyway, all jokes aside, so maximum likelihood. So if this is like my favorite thing, because this is like one of those niche arguments that no one really understands. So if the disturbances are normally distributed, then the beta of a maximum likelihood is equal to the beta of the ordinary least squares. So what in the world are we talking about here? So it's crucial to understand that many statistical software programs like Stata actually perform maximum likelihood estimations for your basic regressions. That's because it's simpler for the computer to do that. And so if you're doing a maximum likelihood estimation and you have, you know, you've met this normal distribution in your disturbances, then you're going to have the same outcome as your OLS. And so a lot of people are confused when they're jumping between these two in like homework and stuff at like the undergrad level, and they're like, why is this doing this? That's because Stata just does the maximum likelihood estimations for basic regressions. And this can confuse a lot of people because the classical linear model's assumptions do not specify the disturbance terms functional form of distribution. But if we add the 6th assumption for that best linear unbiased estimator, then maximum likelihood and OLS basically become the same. And this is crucial when you're trying to use software, as some students do not check whether the disturbances are distributed properly, and they'll actually be getting results from a maximum likelihood and trying to apply them to what they think would be an OLS, and then they're wondering why they have possible differences from something like, and these would be slight differences, most likely, from Excel or something, or even other different types of packages that may use like a raw OLS versus a maximum likelihood. So we're going to wrap this up. By the way, this is the functional form. This is the matrix form. This is how it works. This is what's going on. Matrices is actually a lot easier to do OLS in, even though you'll almost entirely see it in the functional or the linear form. always try to learn stuff in the matrix form because it's just better when it comes to this, especially when you move into time series, because like autoregression and stuff like that, it's a lot easier to understand in matrix. But anyway, to conclude, uh, understanding these assumptions and criteria is crucial when working with the classical linear regression model. So recognizing these violations of these assumptions can guide you in determining whether to apply corrections or use alternative estimators. So it's an iterative process that requires attention to detail, a sound understanding of theory, and a competent data analysis. By doing so, you ensure the robustness and reliability of your findings. And this also goes into what I was talking about earlier. If you're really trying to understand what's going on in these papers and what these people are saying, when they're sending you threads on Discord or Facebook, whatever, and they're like, oh, well, look at this new econometric technique, and this is what this paper said, and this is why you're wrong. It's really good to actually go into that paper, understand their assumptions, understand their theory, and understand how they get to their conclusions based on how they treat the data generating process. Because it's too easy to just take people's word for something, especially in this day and age, right? So what's that famous line? There are three types of lies, or there's lies, damn lies, and then there's statistics, something along those lines. Everybody lies with statistics, so on and so forth. And the case isn't that everybody lies with statistics. This is a fundamentally incorrect look at statistics. It's not that people lie with statistics. It's just that there are like presuppositional theoretical statements being made in these econometric evaluations that, unless you actually read the paper or actually understand what's going on in the theory, then you won't truly comprehend how this works. And I think what's more important than knowing just really the raw math, because the raw math is important because it helps you understand and helps you apply it, but understanding the theory behind everything and understanding that theory helps you understand the econometrics and helps you understand what they're doing with the data generating process. That's why I took so much time in trying to break down this Kuznets curve, right? Because this is important for a lot of these discussions, whether it comes to income inequality, such as Thomas Piketty. One of the biggest, or one of the best criticisms of him is that, well, he's looking at all of this income inequality over this very long amounts of time. And actually, if you map it, it's not a linear function. It's not like income inequality is just continuously increasing. It actually has a lot of ups and downs. Why is that? Well, it's probably something to do with other types of shocks that are happening that lead to increases in income inequality. So when we read his work, Capital in the 21st Century, how much of that is guided by his ideology and his theory versus how much of that is actually motivated by what the data is trying to tell us? And if you watch my video on policy without theory, you'll see that I'm very much against this idea that that any type of these econometric investigations can tell us anything more than what's going on in our own mind, because everybody can read the same data and come to vastly different conclusions. And so we have to understand what's going on in that researcher's and the person who's sending you the researcher's ideological viewpoint, because that is going to quote unquote bias the results in what's going on there. Because again, Thomas Piketty makes some really, really strong arguments. But another way to look at it is to say, hey, no, this is a cyclical nature of increasing inequality, and then some development cycle hits, and then there's a decrease in income inequality, so on and so forth, or exogenous shocks such as technology. As technology takes off, and one type of technology, so you could say like, we could go back to like Victorian times and to the Industrial Revolution. That's going to have income inequality go up because we're going to have the capitalists take over, and the bourgeoisie capitalists, they're taking over. And then we're going to see this impact the proletariats. And then we have some type of counter revolution, I guess you could say, where people are more likely to care about what's going on with the proletariats. And so we could say this is the advent of utopian socialism leading into Marxian socialism. And then we see some more evening out. And then we have like another type of technological or technique revolution, such as like the Chicago School Revolution. And then we see this increasing rate of income inequality until like Piketty drops a book, and then people start caring about the taste of redistribution and stuff. Boom. So now we're coming back down, and there's all these different civilizational ethoses that are getting tossed in here. And so if you're just trying to make an argument from pure data and saying this is what the data says, well, the data doesn't speak. You're giving it legs through your investigation of that data generating process. And that's why it's so important to understand this. And this is why I want to do this series. It's not because I think I'm going to be able to teach anyone better than, again, Lambert when it comes to this stuff. Or even, you could check out some of the videos of Econ John. I think he's got a few on econometrics. I don't think I'm going to be able to explain that better than you, but I think I should be able to be persuasive when it comes to understanding what's going on from this theory-driven side of econometrics, especially whether that's, and we're going to keep opening this up because the next episodes is going to be on each of these different types of assumption violations, and then like what are we going to be doing in response to that. And so if I'm having my assumptions violated to do classical linear regression model, there's a lot more open space for me to have a conversation about what's going on, right? So let's take an example where we're going to be using instrumental variables. There's a lot to unpack in how instrumental variables will impact your regression, and that very well is going to be motivated by theory and your own presuppositional philosophy and how you think it ought to be treated. And that is the key here, right? So if they're using structural equation modeling, why are they doing that? What is the purpose of doing that? Why are they using vector autoregression instead of a different type of time series model, right? Why are they using a panel vector autoregression versus Ariano bond estimator, something along those lines? A lot of that comes down to, one, what's the data generating process saying? Like, will this violate the AB estimation or PVAR estimation? And also, what is the theory behind it? What's the theory trying to get at? Because if I'm trying to get to my conclusions, I'm going to use the estimator that's going to be most biased towards what I want done and what I want concluded out of it. That doesn't make me a liar because the statistics don't lie. I'm not lying when I give you a report or I give you a paper and it says there's no crime, or there's crime is on the rise and it's due to income inequality. That's not wrong per se. That's just one piece. If I open it up and say, no, there's a crime Kuznets curve, then hey, we've just expanded. You didn't lie. You just omitted something. And that may bias the results, but bias may not always be a lie. Because even in your response is going to be biased. Anyway, this got way off track. Not really. This is important. Look, I'm going to be opening up a lot more in this series on like my personal beliefs when it comes to stuff like econometrics, when it comes to stuff like economics, and when it comes to stuff like how people use statistics to lie. I may be looking at a few papers and evaluating what those papers are actually saying, or I really might be looking at a paper and saying, hey, well, this was violation of one. Here's a paper that talks about it. Here's the way they set it up. Here's the way they dealt with it and all of this. And I think this is really important to understand, not the background, but really the application of econometrics when it comes to this, especially if we're trying to be persuasive in the public sphere or whether we're trying to be persuasive with our friends. And let's say our friend is, opposite to our ideology. How are we supposed to explain to them from an opposite ideology what is going on here? What are the assumptions, etc.? And this is usually the place for philosophy. But so many people try to remove philosophy from science, and it's silly. And so I'm hoping that with this video series that we can open all of this up and everyone gets to share in a much better understanding of everything going on. So please like, share, subscribe, check it out for more. This is going to be more of a free-flowing kind of discussion in a lot of these. And I thank you for joining me. I'm the Economancer. Have a good day.